research project on basically the conservation of mechanical energy, which you will understand during this presentation as we get into the article and how this experiment was reduced from that article. So the article that I chose was based on these researchers that were observing the dynamic characteristics of these metallic atoms that are basically being used during a chemical reaction. And so what kind of sparked their interest was that these dynamic atoms hadn't gotten a lot of attention because they're not considered stable compounds. And so there's always been research dedicated to stable compounds and studying stable compounds, but one of the problems with why these dynamic atoms haven't really been studied is because the technology was not available for them to be studied. So recently, the researchers at this Tokyo Institute of Technology has provided this new technology for scanning, and it's a scanning transmission microscopy, and then it's there's also a video-based tracking part of this type of software. It's really cool, but it provides the opportunity to go in and get a deeper look at these atoms and kind of study why they are the way they are. And one thing that really stuck out to me was they kept talking about these atoms, which are metallic dimmers and tremors is what they're categorized as. And what really stuck out to me was how short-lived they are. That they really hit on that in the article, was that they're very short-lived, and that's a big problem for why they're not really able to be studied. And so with this new technology, though, they made a big emphasis on this type of matter being able to be studied at a much higher level, and this would open up a field to possibly open up a field for a new type of matter, basically, because this matter has existed, but it's never been able to be studied on the level that stable matter has been. So, sorry, that was a little much, but that's basically a little bit the rundown of the article. And so these are examples of dimmers and tremors, and I believe these ones were the models were of nickel models, the element nickel. So these are dimmers and tremors for nickel models, and then there's also organic ligands, which are the H2 over here, and also an H2 sulfan tremor is what this is called, which is also considered an organic ligand. Anyway, so the prediction for the experiment. So the article I chose to research investigated the bonding characteristics of atoms during a chemical reaction. And so the dynamic bonding abilities of these atoms have been studied very little, and to understand the qualities of these short-lived structures, their bonding habitats need to be studied. So basically here, it just shows the bonds breaking. Just a little animation right there. All right, so basically this is kind of the introduction of the lab of the experiment that I came up with. So what I really thought needed to happen was the investigation of the energy needed to break these bonds. So maybe we could get more insight of why they are so short-lived. So we're studying whether the energy is conserved before and after the bond is broken, and then investigating the kinetic and potential energy. So to get in a little more detail here, the energy needed to break the bonds between atoms is in terms of mechanical energy, is what we're going to be measuring in this lab. And so you need to be studying whether energy is conserved before and after the bond is broken. And so the concept of work and energy theorem has led to a universal conclusion that an object can possess two kinds of energy, this being kinetic and potential, or gravitational potential energy. So the sum of these two energies is termed the total kinetic or total mechanical energy. And the succinctness of the work theorem, in the form of work equals the final energy minus the initial energy, recognizes as an imperative basic principle of physics to be acknowledged, and this principle is the conservation of mechanical energy, where the initial energy equals the final energy. And so the principle of conservation of mechanical energy states that the total energy of an object remains constant as the object moves, provided that the net work done by the external non-conservative forces is zero. And so the principle of conservation of mechanical energy provides useful insight into the way of the physical world, the way the physical world functions. A little long. So with taking that external non-conservative force out of the equation, we can really study the principle of conservation of mechanical energy. Oh, and then that animation just shows basically that principle, the principle of conservation of mechanical energy, where the potential energy is 10 up here, it remains 0 here, and the kinetic energy is 0 here and 10 down here, recognizes this transformation from potential to kinetic and vice versa. And so a little bit more information here. So to calculate the energy required to break the bond, the two atoms need to be assumed as motionless at an equilibrium separation. And so in this experiment, we will not be using atoms. We'll be using little toys, cars. But these cars are going to be started at rest before any movement or any energy is applied. But they'll be starting at rest. And then if the energy is conserved, the following equation will be true. So as mentioned before, the initial energy is going to equal that final energy. And that initial comes from the kinetic energy, the initial kinetic energy plus the gravitational potential energy, the initial. And then that total final energy is going to come from final kinetic energy and the final gravitational potential energy. And so in this experiment, we'll be using tracker to study the kinetic energy and potential energy of the Hot Wheels car being like shot up a track. And so the different constants will be varied in the experiment to determine what factors affect the kinetic and potential energy. So here are just a couple objectives of the experiment that will be performed, or that I designed. And so we're going to be using a recording device to determine that relationship between kinetic and potential energy, which we kind of already saw. But and then determine that total energy before and after the bond is broken, that total energy immediately after the bond is broken, comparing the kinetic before and after the bond is broken, and then comparing the mechanical energy of the two atoms, in this case, the two cars. And so the materials that are going to be used during this lab is going to be the tracker software, a cell phone to video the cars going down in order to put that into tracker for it to be analyzed. It's going to be used a string to pull that car up, a ruler to scale, which helps when analyzing the video in tracker, and then a Hot Wheels car, which is going to be like the atom, and a scale to measure the mass, and then a Hot Wheels track for the car to go up and down. And so here's just like a little pre-lab question, which is what's the following circumstances will mechanical energy not be conserved? And so that answer would be D. And that's because the force is not being conserved. And so here is a little bit of what the setup would look like. I'm going to go over the procedure of how this experiment is going to work. So the two Hot Wheels track would be something kind of like this. They'd be set up so they're opposing one another, and they want to make sure that the same height, so this is kind of resting on that box right there. So we want to make sure we have equal heights for both of the tracks here, because that first trial, we're going to be measuring them at the same height, same mass, same length. And so you want to set up the camera like maybe around here so it kind of catches that entire track part right here, because you want to get both cars. And so I want to make sure I measure the mass of both the cars before performing the experiment. If one car happens to be like a little bit less than the other, can always add a little bit of weight with the clay. And then each car should have like a string attached to it to give it that tug to pull it up there. And so here is an example of what that kind of would look like. You want to make sure that the string would not be like interfering with the wheels. I didn't do a very good job, but so maybe more down here. The thinner string would be ideal, but the point here also is that it's not going to be pulled at a constant velocity. It's going to be given a tug, so it's going to go up quickly, and then so we can see that energy as it goes up and then travels back down. Sorry, I'm getting ahead of myself. Anyway, so measure that mass, make sure that each car has the same mass, a string attached to both of them, and then measure the length and height of the track and make sure to record that in a lab notebook, and then practice giving both those cars. Ideally, you'd have a lab partner to do this with, but give that car a tug, and then once you tug that once, you don't want to apply any more force, and so then that it's going to start down here, give it a tug, go up, and then it's going to roll back down. And so that video camera, you want to make sure you start it before you give it a tug, because then you're not going to capture that whole motion. And so you make sure you start that video beforehand, then have it shoot up, and then it's going to go back down, and then you can stop the recording once it's reached the bottom and it's no longer moving. And so you want to, after you get all those videos, you want to go ahead and put them into the tracker so you can obtain the velocities of the cars before and after they're separated. And then also want to obtain the velocity of once the car reaches back down the hill when it's at the peak, because this will help us to calculate the kinetic energy and gravitational potential energy. And so this whole process is going to be repeated 3 more times, changing one constant with each trial. So that's why we have 2 cars here. One car is going to remain constant as like a control, and then the other one is going to be varying in mass, length, and height. So for one trial, the mass will vary while the other 2 remain constant. Second trial, the length will vary while the other 2 remain constant. And then the last one, the height will vary with the other 2 remaining constant. So here's just kind of an example of what the data tables would kind of look like. So you'd have your 2 cars here. You'd have like whatever labeled car 1, car 2, or car green car, red car. And then you would have that mass that you measured for both of them, that length of the track, and then that height. And then this one gets a little bit more complicated, but so once you get those videos for the motion of the car being measured, you would go ahead and plug in those initial and final velocities, which you can get from the graphs in Tracker. And then once you get that velocity, as we see here, you can go ahead and find that kinetic energy. So you want to do that for the initial and the final kinetic energies. So the initial would be when the car is at the bottom of the track, and that final would be once it's at the top. And then it's same for the gravitational potential energy. So that initial gravitational potential energy will be when it's at the bottom. That final is going to be when it's at the top. And then from there, you can get that total initial energy and that final initial energy, which you'll just be using simple addition by adding up that final kinetic energy and then that final gravitational potential energy to get that final total energy there. And the same is done for the initial, but with the initial ones. And again, using these equations, you don't really need anything besides for the potential. It's a little bit easier. You don't need to do any of the tracker with this to calculate the gravitational potential energy. It's just going to be your mass, your gravitational constant, and then your height. And yeah, so that's just kind of an example of what that would look like. And then we have the discussion and results. So these are just like a couple example like questions that could be used to kind of interpret those results, go on a deeper level, and discuss what they mean. Like you see here is the energy conserved before and after the car climbs the hill. Provide the data that you collected in your lab notebook to support or disprove that. And then which of the total energy is larger, the final or the initial, kind of a trick question there. And then you have when is your kinetic energy lowest, when is it the highest, same for the gravitational potential energy. And then how was the other car affected by changing the weight and the height and the length, and then constructing a graph of the position versus energy to demonstrate how the kinetic and potential energies are related. So that's kind of what this is here. This gives an example of kind of what we'd want to see. This is not exactly it, but because this kind of shows more of a simple harmonic oscillator example, but it still can be used to explain what we're trying to see. But so basically this green line here is our total energy. This red represents the kinetic energy, and then this blue represents the potential. So you can see here at the equilibrium position. Oh wait, did I say that wrong? No, I didn't. Never mind. Sorry. So yeah, potential, kinetic, and then total is green. So down at the bottom is the equilibrium position, which would be equivalent to when the cars are down at the bottom of the track, where the two tracks meet down at that bottom. That's the equilibrium position. And you can see here the potential energy is equal to 0, which is exactly what we want to see. And the kinetic energy is at its highest point, which is also what we want to see. But as you can see here, we're still getting the same total energy because the kinetic and potential are being transformed from one to the other. So here the kinetic energy is at its highest and the potential energy is at its lowest. However, once we get to the top of the track, once the car is given that little tug, you can see the potential energy is at its highest, but the kinetic energy is at its lowest. So you have this high point for the kinetic and then this low point for the kinetic. So here at the bottom, the kinetic energy is being transformed into potential. That's why it's at this high value here. However, once we get back down to the track, so here we start the car here, we give that at that initial little tug, it comes back up here. However, once it reaches that top of the track, it's going to come back down. And then again, we get the potential energy is at 0 and the kinetic energy is at its highest point. So that potential is being transformed to the potential is being transformed to kinetic being transformed to potential. Again and again, it's the same thing, and that total energy is going to remain the same because we are just transforming from kinetic to potential. We are not losing or gaining energy. It is just energy being transformed from one form to another. All right, finishing up here. So the overall results of the computer's gonna die. Oh gosh. All right. So the overall results that we would want to see from this lab to demonstrate that there's no change in the total amount of mechanical energy, so hence it is being conserved. And so the forces doing work that are involved in this experiment are completely internal, and so the total energy of the object does not change. And so with this type of experiment, the sum of kinetic and potential is everywhere the same, as we saw with that graph before. So when the potential energy increases due to the height of the car at the top of the track, the kinetic energy is decreasing from the car, slowing down. Kind of explained that in the past slide. again, so once the car reaches the top of the ramp and slides back down, the kinetic energy will increase and potential energy will decrease. And so the energy transforms its form from kinetic to potential and vice versa. So the data from the car with the varying constants, the data should be increased in magnitude, but the energy is going to be conserved regardless. So what I mean by this is when we increase the mass of that other car, it's going to increase the kinetic and potential energy. So looking at this equation back here, so we have the mass here and the mass here, so it's going to increase the magnitude. However, it's not going to change whether energy is going to be not going to be conserved, or if it is. The energy is still going to be conserved, and the values are still going to be transformed from one to another. The magnitudes are just going to be greater. The same goes for the height and the length. So the magnitude of the kinetic and potential will be different, but the whole thing here of transforming from one to another and kinetic and the mechanical energy being conserved is going to remain the same. The mechanical energy is still going to be conserved whether these magnitudes are less or greater. And so we'll go back to that. So this is like a little what's it called? Equation of the conservation of mechanical energy. So this would be the total initial energy. This is going to be the total final energy over here. And so by changing the mass, it's going to increase these values. But this statement here, this equation, is still going to remain the same. Because the energy is still going to be conserved with the car going up and down the hill. So looking back at the article, we can use these same skills that we practice in this experiment, they can be applied to measuring the energy required to form and break bonds. Not exactly on the level that we did with this experiment. There would have to be more the chemistry side involved, and more of the chemistry side would need to be incorporated into the experiment. For example, determining like whether the reactions are like endo or exothermic is pretty crucial for determining how much energy you're going to get. And then, but both endo and exothermic reactions involve breaking and require energy to do so. So that's how we can kind of relate this experiment to that. And so breaking bonds is always going to take energy, and by understanding the energy required to break the bonds provides a better understanding of the atoms involved. And so studying the study of the atoms involved, meaning the study of the dynamic assembly between the atoms during the chemical reaction. So actually that didn't make much sense. I mean, the atoms that were mentioned at the beginning of my presentation, the ones that need to be studied, the short-lived ones, the ones that are being assembled during the reaction that don't get a lot of attention. So by understanding the energy, like how this works with breaking bonds, and whether that energy is conserved or non-conserved during the breaking of the bond. So just trying to understand that by doing experiments like this provides more insight to those short-lived atoms, to those atoms that are assembled during that chemical reaction. And so that is basically it. And then here are a couple references. These are all websites with the link is like, if you click on it, it goes straight to the link. Is these, and then this is the book I used. But that's pretty much it. Thank you so much for listening, and hope you learned something. Thank you.